Good evening, sir.
Good evening, how are you? Hello.
Yes, sir.
Can you hear me now? I'm audible, right?
Yes, sir.
So, how are you?
Good, sir.
So, we are done with electric field, and now we'll do electric flux. Okay. Electric flux. First, we'll see the definition here, what it means, and then we'll see the mathematical definition, the most important concept here, and then electric dipole is there. Also, and this flux. Okay, let's do electric dipole first, then we'll do the electric flux.
Okay.
Because then will be it will be continuous. First we'll do electric dipole. Because electric flux and Gauss law are totally related, so we'll do the related topics together. Electric dipole. A system of two equal and opposite charges are called opposite charges is called electric dipole. So if there is minus Q charge, this is plus Q charge. So the system of two charges, something like this, is called electric dipole. What is the total charge? Hello.
Yes, sir.
Yeah. So just here, net charge on a dipole is net charge on a dipole. Now, when we say that we are talking about dipole, then we will think of these two charged particles together. There is no line, right? I'm not using this line. There is no line here. Just there is a system. These are just two charged particles, and together they are called dipoles. They form a system. They must be taken together all the time. So if we take these charged particles together and a distance between them, let us say that distance between them is, let us say that d. So net charge on the system is always plus q minus q, that is 0. Net charge is 0. But when we say that, but by definition, we say that charge on a dipole is charge on a dipole is charge on the charge of positive side. So
Okay.
here, for example, what is the charge here? What is the charge of dipole? Plus q, right? Charge of dipole will be plus q in this case. Whatever is the charge on the positive side, that will be called the charge on the dipole. And just see this thing. There are certain terms that we need to define. There is
So it won't be zero. The net charge is zero, but charge in the dipole is the positive charge.
positive charge, positive q, right? So whenever the system is of plus 2 coulomb, minus 2 coulomb, so plus 2 coulomb will be the charge on the dipole, right? That will be called charge on the dipole. And then there are certain terms that we need to understand. Dipole length. Dipole length is a vector quantity. Or let us, instead of d, let us just define it as L. So dipole length is defined as the distance between the length, a vector of the distance, the separation between them directed from negative to the positive side is called the dipole length.
Okay.
How to define it? Like the simply that the separation between the charged particle between the opposite charged particles is called dipole length.
Okay.
It is a vector quantity. Direction its direction is given by from negative to positive side. Now there is dipole length, dipole moment. Dipole moment P is defined as P is equal to Q L vector. It is defined as the product of the charge on the dipole and the dipole length. That's it. Okay, so these are the definitions that we need to remember while having the discussion on electric dipole. Now, we will talk about the physical significance, because in this next chapter also, electric dipole will be discussed in the next chapter also, but I would like to discuss these things here.
When I'm not able to hear you.
Not able to hear me? Hello? Hello?
Yes, sir. Yes, sir.
Am I
Now
audible
I'm
now?
able.
Yeah.
Yes, sir.
Okay, okay. Okay, just see that physical significance of dipole moment. What do we mean by dipole moment actually? Just see physical significance of dipole moment. Dipole and dipole moment. Just see that usually we don't come across this kind of dipoles, but we define dipoles like this, but usually we don't come across dipoles like this. um like there is a separate charge minus q and there is a separate charge plus q. This kind of separation is not possible in the real world. Real world, what kind of dipoles are found? For example, any atom can be treated as a dipole. Just see this thing here. Let us say that an isolated atom. What is the shape of an isolated atom? Isolated atom means it is free from the forces by other sources. So if there is an atom, it will be completely spherical, right? Here there will be positive charge at the nucleus and there will be electron cloud around it, right? Something like this. This will be the thing. So here, uh, this is the isolated atom, completely spherical.
Okay.
Completely spherical. This is the thing. So in this case, here what happens, there are certain things. Center of charge, center of charge of positive and negative charges coincide. It means, what do we mean by center of charge? Now here we need to understand center of charge. So just see the concept of center of charge is something like this. Center of mass, do you remember center of mass?
Yes. The place of the mass of the body is concentrated.
Yeah, suppose these are the three masses, M1, M2, M3, and this is the x-axis, y-axis. What is the center of mass? How do you find out the center of mass? XCM.
We first coordinate x.
Or very simple,
X.
just yeah, just see this. We will say simply r vector is equal to m1 r1 vector plus m2 r2 vector plus m3 r3 vector by m1 plus m2 plus m3, right? This is the thing. This is your center of mass, definite position vector of center of mass. Center of mass. Exact same thing. Exact same thing. You have to define it. Center of mass, center of charge will be defined in exactly the same way. Center of charge. Just like this thing, if we have like suppose Q1, Q2, Q3, Q1, Q2, Q3, then center of charge will be defined as, sorry, in this case, instead of M1, you will use Q1 R1 vector plus Q2 R2 vector plus Q3 R3 vector divided by M1, sorry, Q1, Q2, Q3. Exact same definition. Q1,
Okay.
Q2, Q3. Now just mind it, center of charge and center of mass can be different. Center of charge has nothing to do with the mass. It simply means that how the charges are distributed around in a particular system, how the charges are distributed, right? Representation of it is simply the representation of, it simply represents how the charges are distributed in a system. That's it. Center of mass tells you how the masses are distributed, individual masses are distributed in a system. Similarly, this thing, right? So center of mass. So in this case, just see that there may be possible that there may be some positive charges. Let us say that now center of charge of positive mass. Like suppose there is a positive Q1, Q1, Q2, Q3, Q4. Let us say this thing. Let us say that this is positive, this is negative, this is negative, this is positive. So center of charge of positive charges will be here. Let us say that it is also negative, Q5. And if the center of mass of, or let us say that this is Q6. Suppose we did this thing, this kind of thing. And the center of mass of positive charges comes out to be here. Center of charge of positive charge also comes here, and negative charge also comes at the same position. In that case, net dipole moment of this thing, in that case, if center of positive and negative charges coincide,
Taken separately.
yeah, it means they are coincide, right? Center of positive charge is also at the same point.
Separately, and the center of negative charge is taken separately.
Yes, separately, right? Calculate the positive charges separately and calculate the center of positive charges separately, right? Then if they come out at the same point, then dipole length will be 0. dipole length would be simply 0 because it is the separation. In this case, dipole length will be defined as what? In this case, dipole length will be defined as the separation between the center of positive and negative charge. Is that understood? If they coincide with each other, dipole length will be 0. Very simple. So in that case, dipole moment will be equal to what? That is 0 vector. Dipole moment will also be 0. Clear this point? So
Okay.
in an isolated atom, just see that it is spherical. Electrons are uniformly distributed all around. You will assume this thing. So it means center of negative charge also comes at the center of the sphere, and the center of positive charge is already at the center. So in this case, what is the dipole moment? Net dipole moment is equal to 0, right? In this case, dipole length will also be 0 in this case. So an isolated atom has no dipole moment, no dipole length at all, because their center of positive and negative charges coincide with each other, right? That is one point, very important. But just see that what changes occur, right? In presence of an external electric field, an isolated atom in the presence of an external electric field. Now let us say that uniform electric field is there. Uniform electric field is there. And I want to take there is an atom. Now, in this case, tell me if there is a positive charge here and if there is a negative charge here at this point, what will be the direction of forces on it? Right, left. On positive Q, force will be right or left. We don't know where are the charges, right? Only the field lines are given.
On positive Q towards the left.
On positive towards the left, right? You're saying this thing, this way, right?
Yes.
Okay, that's wrong, right? Let's just clear this concept. Just see that, remember this formula. F is equal to Q E vector. I told you this thing, right? F is equal to Q E vector. At this point, what is the direction of electric field? In this direction. Electric fields are directed in this direction. So force will be equal to what? Simply Q times E vector, right? It is in the same direction, only the magnitudes will be different. Q times E. So force will be in this direction in this case. So here, force is in this direction. But here, force will be in this direction. Because minus QE.
Oh, okay.
Yeah, this thing. This is minus QE. Here, when you're using the vector sign, then you have to use the sign of the charge. While calculating the magnitude, I told you do not use the sign, right? Be careful, very confusion. So when you already know the direction, then you do not need to use the sign of the charge in the calculation of the magnitude. But if you don't know it, if you're using...
When should we not use the sign?
Yeah, here you have to use the sign. While in the calculation, when you're only dealing with the magnitudes, you don't have to take the signs, right? So this is the thing. It means positive charge will experience the force in this item. Both the positive and negative charges will experience the force in opposite directions, right? Now just see that in this isolated atom, positive charges are here and electrons are distributed all around. What will happen actually? In this case, negative charges will be just pulled in this direction. These positive charges are on one side and the negative charges are accumulated on this side, right? So this side, so now if you calculate this thing, if you see, now the center of negative charge will be here. This is the center of negative charge and this is the center of positive charge. And now there is a separation between them, right? This is L vector. Do you see this thing? It means shape of the atom changes. Shape of the isolated atom changes. Because of external field, right? In an external field. This much you understood. This is very important. Initially, when there was no field, center of positive and negative charges were all at the same position. Right? Here, there was no problem. But when you expose it to, when you place it in an external electric field, then negative charges are pulled on a different direction and the positive and negative charges are separated from each other. And due to that thing, an external electric field, here we can say that due to an external field, a dipole moment is induced in an atom. A dipole moment is induced in an atom. Induced in the atom. This phenomenon is known as polarization. Polarization. It means inducing dipole moment on individual atoms is called polarization. In electricity, right? Electric polarization. There is an optical polarization concept also. That is a different concept. This is electric polarization. Polarization means simply you're inducing a dipole moment, which was not there before, right? Initially, when isolated atom was there, dipole moment was zero. But the moment you place it in an external field, the center of charge of positive and negative charge will be separated. And because of that thing, external you can say that an induced dipole moment is induced in. Suppose if you turn off this field, this atom will again come back to the same shape. Right? If you turn off this field, it will again become spherical. So this shape will last as long as the electric field lasts. That is the thing. So electric field is inducing this dipole moment. That is why this is called polarized dipole moment. So this dipole moment here, P will be equal to what? Q L vector. And here Q is what? All positive charges. All positive charges. Very simple. And this is called polarized dipole moment. Understood this much?
Okay.
Yeah. So we will talk about this thing and First, we'll talk about dipole, how a dipole behaves. Now just see that why dipoles cannot be separated from each other. Because electrons and protons are the part of the system, right? And that atom behaves like a dipole now. That is the actual dipole in the reality. So in reality, we don't come across that there is a separate positive charge and there is a separate negative charge. They are not a part of anything solid. But here, just the atom is one single system, right? It contains electrons and protons. Electrons are set of all negative charges and protons are set of all positive charges. And they form a complete system. You are just changing the distribution of charges and then you're inducing a dipole moment in it. Clear this thing? Center of charges, center of charges. So this kind of things are very, very obvious. Most of the time, we'll be coming across this kind of dipole moments when the center of positive charge and the negative charges are separated from each other, and that's why the dipole moment comes into picture. Okay. But the basic concept, you always remember this thing, right? Imagine minus q to be separate and plus q to be separate. Distance between them is dipole length. Direction of dipole length is minus q to plus q. Minus to negative side, right? Minus to positive. Negative to positive. That's it. Understood this much? Okay.
Yes, sir.
Now we will calculate the field of an electric dipole. Now, these derivations that we are going to do is very important from exam's point of view. They are directly asked, right? And if not asked, many problems are given based on these derivations. Field due to a dipole.
So the L vector, it refers to the length.
Yeah. Separation between positive and negative charges. Once again, just see that if you're confused. In the case of atom, dipole length is what? L vector is what? The separation
Zero.
between center of positive and negative charges, right?
Okay.
This is the thing. And in reality, this is how we define. Dipole length is simply the separation between the opposite charges. That's it. Let us say that there is a dipole. Okay. Something like this. Let us say that this is x-axis and this is y-axis. This is minus q, this is plus q. It is a dipole moment, dipole. And let us say that for the sake of simplicity, what we'll consider, this is the midpoint. We will take the origin over here and we'll consider this distance to be a and this distance to be a. So total distance is dipole length will be equal to what? L will be equal to what? 2a. Dipole length, right? This is the dipole length.
Okay.
Dipole length. So therefore, dipole moment will be equal to what? I'm just using the property here, like magnitude only. E is equal to what? Q into L. That is 2qa, dipole moment. So we'll be using this criteria. Why? Because in terms of A is the A is what? Half of dipole length. A is half of dipole length. So we'll be using this thing. We'll be expressing the electric field due to a dipole in terms of A and this thing, right? There are two things we'll be calculating. Suppose this thing is called axis, and just see that this is called perpendicular bisector.
Yes.
Perpendicular, yeah. Perpendicular bisector can take this thing. But just imagine, instead of perpendicular bisector, I am imagining a plane. Just perpendicular to this line. You see this? If there is a line like this, perpendicular plane like this, perpendicular to this thing, right? It is something like this. So
Okay.
this is perpendicular bisector. And just see that in this plane, any point is equidistant from these two charges. Isn't it? If this is R, this will also be R. Just see this thing. If you place this thing in the middle of hand, any point on your hand is equidistant from the two ends of the pen. Getting it? Right or left? You can define this thing here. This point is also equidistant from the, although in the two dimension, it's not very clear. But these two distance are
I don't
exactly
understand this point.
okay.
I don't understand how to equal.
Okay, this is a bit difficult to understand, but it is very important to understand here, right? Just see. Equatorial plane. Here, one thing, just remember, this is called equatorial plane. First, just note down these things, important terminologies. Equatorial plane. This is called axis. So, equatorial plane is what? The plane passing through the origin and perpendicular to the dipole length. The plane perpendicular to the dipole length and passing through the origin. Passing through the midpoint of the dipole. Clear? This thing, that plane is called the plane which is passing through this thing. Okay, now how will you do this thing? Yeah. Just imagine a pen over here, and then you place your hand perpendicular to this thing, right? From the midpoint. And just imagine any point on this plane is equidistant or not from these 2 points. They are equidistant. Yes. Any point is equidistant, right? Yes. Not just the perpendicular line, but any point is perpendicular, equidistant from this thing. So that is why we are talking about this thing. Here, very important point. Here you have to understand this point. Any point on the equatorial plane is equidistant from plus q and minus q, right? They are just the two ends of the things. So they are just equidistant. Any point is equidistant from this thing. So just see this thing here. There are two terms we'll be using: axial points, the points on the axis, For example, I can say that this is the point P. For example, P is the axial point, right? P can be, or I can say that Q. P and Q are the axial points. PQ are the axial points. You can take it anywhere on the axis, right? X-axis, you can take any point that will be axial points. And therefore, there is one for equatorial points. Equatorial points. Points on the equatorial plane. So you can think about any point. For example, this is A, this is B, or this is C. A, B, C. These are equatorial points. Clear this basic concepts? We are expressing dipole moment in terms of A, and what do we mean by axial points, equatorial points? Any point on the equatorial plane is equidistant from plus q and minus q. Is that understood, this thing?
Okay.
Okay, now we will calculate the electric field. Just keep these points in mind. Electric field at the axial points. So let us say that this is minus q and this is plus q, and there is the midpoint here, and we will just expand the axis in both the directions. X is something like this, and we want to find out, this is my origin here. I want to find out the electric field at this point. Let us say that this is okay, let's take the NCRT point. Let us say we take the electric field here, point P. Okay, in this case, tell me what will happen. Last class, I told you some ideas about this thing. Whose field will be stronger? There will be two fields over here. Field due to plus Q and field due to minus Q. Both the charged particles will create an indivisible electric field at the point P. Plus Q will create an electric field in this direction. E plus Q. Or let us say that, let's just talk about magnitude. And minus Q will it will be slightly weaker. E minus Q, right? Net electric field will be in which direction? Plus Q is greater, right? E plus Q is greater than E minus Q. So net electric field will be in this direction, isn't it? Net
So
electric
every time
field.
will be in the positive direction.
Sorry.
So every time net electric charge will be in the net electric field will be in the positive direction.
Yes. Because how do we find out the direction of electric field? I told you, imagine a plus 1 coulomb of charge over here. Which direction the force will act? Last class I told you, right? This thing. So due to positive charge, and you know this thing, E is equal to KQ by R square. This formula we were talking about last class. Source charge, right? This is the thing. This is the source charge. And what is the field due to this thing? Can you tell me what is E plus Q? E plus Q is equal to how much? Magnitude. Use this formula. Tell me, okay. One thing I didn't give you this thing. Just a second. Here, you will take the distance from here to here as no. Here, all the distances will be measured from the origin because we have chosen our origin at the midpoint. Just say that, let us say that this point is at R distance away. From this thing. We know that this is also A, this is also A. Okay. So R1 is equal to what? This distance will be R1 due to plus Q charge, and this distance will be R2 due to this thing. And can you see this thing that R1 is equal to R minus A, and R2 is equal to R plus A. Is that clear? Where R is the distance of P from the origin. First, understand this. Tell me if there is any confusion.
So I'm just getting confused within the axial point. It should lie on the equator, so it should lie on the axis, right?
Yes. Yeah, it is. I'm just talking about distances, right? R2 is just a distance. Line is exactly this thing. I'm talking about what is this length? That is
Okay.
R minus A, right? Is that clear?
No, I just don't understand how is the plus Q electric field greater.
Okay. Just see that P point is closer to plus Q, right? Here, from this thing, electric field is inversely proportional to the square of the distance. Closer it is, the stronger it will be. P point is closer to plus Q charge, right? Look at this, P and plus Q. They are closer to each other. And minus Q and P point, they are so much distance away. So field of plus Q at P will be greater and field of minus Q at P will be smaller. What is the confusion here? Okay. If, let me remind you of this thing. If there is a source charge plus Q, this sets up field in all directions, right? You know this thing? It was getting smaller and smaller and smaller. You remember this thing. What does this imply? This implies that electric field is decreasing with distance. E is equal to kq by r square. As r increases, E will decrease. Yeah. First, look at it carefully and tell me which part is not clear, right?
Okay, sir, I understand.
Right? Simple. P point is closer to plus Q. That's why field due to plus Q will be stronger here.
Okay.
P is distant away from this. If I had taken this point here, you see that what would be the case would be opposite, right? In this case, then this will be greater. E minus Q will be greater and plus Q will be smaller, right?
Okay.
Now you got the point here. This point is closer to plus Q. That's why E plus Q is greater. You understood this point, right? This thing?
Okay.
So now let's just try to calculate these points. So EP is equal to, we need to calculate this thing. Just see that. Clearly, EP is equal to E plus Q plus E minus Q. One thing you have to take it as positive. So rightward vector, you have to take it as positive and leftward vector, you have to take it as negative. Okay. In this case, because they are one-dimensional vectors, so in one dimension, we can take care of direction by positive and negative sign. So no need to use the vector sign here. Clear this thing? So in this case, first you tell me this thing. EP is equal to what? The net electric field at P will be equal to E plus Q minus Q. What is E plus Q? Now you decide. You tell me. Derivation is not that difficult. You just need to follow along. Use this formula, KQ by R square, very simple. KQ by R square source charge divided by the distance of the source charge from the point.
QQ by R minus A square.
Correct. KQ by R minus A whole square. Okay. Similarly, E minus Q will be equal to what? Don't put negative sign, right? Because we'll take care of it with the help of directions. Simple. Source charge is now this. Where are you confused? Tell me. This is very straightforward. You do exactly the same thing that you did over here.
So I understand. KQ by R plus A the whole square.
Yeah, that's it. KQ by R plus A whole square.
So the
Anything
distance of the distance from the point.
Okay, distance, right? Here you're getting confused. R1 is equal to R minus A. R2 is equal to R plus A, right? This is the
Oh,
thing.
so the distance I understood. So it's a distance between P and plus Q and P and minus Q.
Yes, because
Okay. The place
that is
I
what.
was getting confused, so it's calculating this distance between plus Q and minus Q.
No, 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 no. In this electric, just that is what the meaning of this formula, right? Just see that. What is the meaning? What is this R? R is the distance of source charge from the point where we are calculating the electric field, right? So that
Okay.
is what you have to do here. You need to know the meaning of this formula and that you apply over here. Now it's very simple. Therefore, EP is equal to E plus Q plus. Okay, now let us just do this thing. Should we plus it or minus it? Which one is greater? E plus Q is greater, right? And they are in opposite direction. Just see that in this case, what is happening? E plus Q is on this side, and E minus Q is on this side. Which one is greater? E plus Q is greater, right? Net electric field will be in this direction, but we will do E plus Q minus E minus Q. Fine? That's it.
Okay.
We will just subtract this and we'll get the value of this direction. So KQ by R minus A whole square minus KQ by R plus A whole square. That's it. Now just simplify this thing. KQ constant, common. We can say this thing, R plus A whole square minus R minus A whole square divided by R minus A whole square R plus A whole square. Is that fine? Now just
Okay.
expand it and you will see this thing. This will be 4AR, I guess. AQ, this will be 4AR.
If we expand it.
Yeah, if you expand it and cancel out whatever is cancelable, right? Or you can do this. Just see this thing. Let's just do it. R square plus A square plus 2AR minus R square minus A square plus 2AR, isn't it? And then this will be equal to, do you know the formula? A minus B, A plus B identity, that is A square minus
Sir.
B.
Yes, sir.
So this is R square minus A square to the power whole square. So here this term getting cancelled. So you are getting KQ4AR divided by R square minus A square to the power whole square. This is your general EP. But the job is yet not done. What we are going to do, let's not mark it here. Can we write it 2KP 2R divided by R square minus A square to the power 4. This is EP. General electric field at any at axial point. general expression for the electric field due to our dipole at the axial point.
Okay.
This is the thing. Now there is one very important thing which is asked. If R is much greater than A, then we can simply neglect A square. It means A is very small, right? A is very small. It is something like this. If their dipole is this length, and we are calculating the electric field here somewhere here. So from this distance, this will appear to be a point charge, right? Something like this. That small distance will not even be visible. Just like a very big car appears to be a very tiny object from a very large distance, right? Similarly, at calculating the field at a very great distance, then this dipole would be just a small, a tiny object, right? Just a system, just thing. And this small difference between their dipole length will be totally negligible. That is the thing. So in that case, what we will be doing, what is the field then? This will then, field will become, EP will become 2 kp r by r4. A square will become totally zero, right? In that case, because A is negligible, because A square will come out to be zero, approximately zero in this case. Negligible or not zero, we will simply say that negligible. Negligible. Only R is very large. So now you cut this part, you will be getting EP is equal to 2 kp by R cube. Understood this part?
Okay.
So can you derive it yourself? Not very difficult, right? If you just know the individual concepts, you can easily derive this equation. The field at any equatorial point. Now, just once you know this concept, so mostly this thing is asked in the exam, right? What is the electric field at large distances? Like, if just see that here, you need to understand this thing, that if there is a charged particle here, minus q plus q. A, this is origin. Now tell me at any point here, what is the direction of net electric field? Just here, in this case, I have directly written it.
Right.
Yeah, here I have directly written it P. P is equal to what? 2QA. I've just replaced it, right?
Yes.
That is P, right? Simply. So in this case, just tell me here at this point P, what is the direction of the field? Net electric field. It is in the right or the left? Right or left? Net electric field will be? In order to do that, just always imagine this point P is closer to plus Q, right? The point I was illustrating. This point P is closer to plus Q. Electric field due to plus Q will be greater, E plus Q. And electric field due to minus q will be slightly smaller. Got it? So net electric field will be equal to what? Suppose this is applying 10 Newton force and this is applying only 8 Newton force. So net force will be acting in which direction? This direction 2 Newton force, right? Net force will be 2 Newton force. 8 Newton are balanced, and the unbalanced force is only 2 Newton force, which will produce acceleration in that direction. Is that clear? This thing? So net electric field is that direction. So very simple. Now let's just forget about this thing here. So net electric field will be in this direction. EP will be in this direction, vector. Clear? And at any point here, it will be definitely to the right. Now tell me here, what is the direction of electric field, net electric field in this, at this point? It was P. Let us say that it is A. Net electric field is in which direction?
That's right.
To the right. Why? You see that this point A is closer to minus Q. So net electric field will be greater. And plus Q, due to plus Q, this will be smaller, right? It is still in this direction.
Okay.
Right, this point. It means, and what is the direction of dipole moment? Tell me. Dipole moment is a vector quantity. P is equal to what? 2
L vector.
Q A.
Right.
Yes, correct. If I just simply Q L vector, right? Simply, this is the thing. This is in this direction to the right. It means dipole moment is also to the right. It means, just see that electric field, net electric field is in the direction of, clearly, net electric field is in the direction of dipole moment at any point on the axis. Understood this point? It means we can write,
Yes.
therefore we can write vector form of the electric field. We can write that EP vector is equal to 2 kp by r cube p cap. Clear this point?
Okay.
This is the final derivation. This is very important, right? This is very important. So that is what you have to know. So the electric field at any point on the axis is always in the direction of dipole moment. Clearly, you can write this thing. Electric field at any point on the axis is always along the dipole moment. Along the dipole moment. Clear this thing? And magnitude is given by this thing, 2 kp by r cube. One thing is very, very important. Just see that due to a point charge, field due to a point charge is equal to what? Kq by r square. And field due to a dipole is equal to what? 2 kp by r cube. This is coming, right? This is the thing. So it is different. Like just by looking at it, you can say that whether it is the field set up by a dipole or a point charge. This is a point charge. This is a field due to dipole.
Okay. Oh, here P stands for
Dipole,
2QA.
dipole moment, dipole moment. P stands for
No,
dipole
the
moment.
2Q.
Okay, dipole moment. Dipole moment is a vector quantity, P vector, and P cap is the unit vector along dipole moment.
Okay.
So field due to a point charge is this, and this is field due to a and just see that field due to a dipole. Clearly see what is the difference between them. Sometimes questions are what is the difference between the field due to a point charge and a dipole. So this is the thing, right? This is E is inversely proportional to square, but here E is inversely proportional to the cube of the distance. It falls faster, right? In this case, in the case of dipole, so it is faster in this case. So electric field falls rapidly due to a dipole at larger distances. So this field, just say one more thing you have to remember, this field is valid for R is much greater than A. Okay, R is much greater than A. Not for if you're coming very close to this thing, like then this formula will be used. Like suppose if you're calculating the field, suppose you're calculating a field at this point. So you're close to this thing, right? Plus Q and minus Q, you're very close to this thing. Then you will be using this formula. This formula. But if you're using, like suppose the point is suppose here, or maybe it is here, then you will be using this formula directly. And in most cases, you'll be using this formula only.
Okay.
Because dipoles normally are very small, right? An atom is so small that any distance is very large distance for them. Like that is it. Clear this point? So that was
Yes.
a field due to a dipole. And there is a special representation for this thing. We will write Ex is equal to 2kp by r cube. Just remember this thing, right? This is field due to axial point. Okay. Now the next point we will talk about this thing you also can find out. Just see. Equatorial plane. This is the equatorial plane. Again, this is minus q. This is plus q. Now just imagine the point to be here. This is the point P now. Okay. Now here we will do this thing that let us say the field due to minus q will be in which direction? Tell me. In this case, let us just change the sign. That will not change anything at all. Let us say that this is minus q plus q. Plus q and this is minus q. Then field due to plus q will be in this direction. Just see that they are equidistant, right? They are equidistant. And we will take, this is the origin here. The distance of P from the origin is taken as R. This is A, this is A. So let us say that this is A and this is B. What is AP? Tell me what is AP? Length of AP will be equal to how much? Or very simple, not AP. Let's just
A square plus R square.
Yeah, correct. So we will be taking this R1 and this is R2. Distance of plus Q from P, distance of minus Q from from P. So R1 is equal to what? Tell me. Yeah, it is a right angle triangle. So from this triangle, you can easily guess what is R1.
Yes, root A square plus R square.
Correct. So R square plus A square. Similarly, R2 will be equal to what? Same thing. R square plus A square. Yes. Now let us say that this sweeps an angle theta, and both the R1 and R2 are exactly equal. They just see this thing. They are exactly equal, right? They are exactly equal. So this is an isosceles triangle. So this angle will also be theta. If this is theta, this will also be theta, right? Same angle, isosceles triangle. So now just see. Tell me what will be the direction of the field E plus Q at P? Which direction? E plus Q will be in which direction? Here is your plus Q. And this is the point at which you have to find out the field due to plus Q. You're getting confused here?
Yes, sir, a bit.
Very simple. Just if there is a plus Q charge, and I ask you what is the field at this point, first you will join the point, right? And you will imagine a plus 1 coulomb of charge over there. Plus coulomb of charge will experience the force in this direction. That will be the direction of field. If the source charge happens to be a negative charge, and you want to calculate the field over there. Now, if you imagine a plus 1 coulomb of charge over here, plus coulomb of charge will be attracted. In this case, the direction of field will be in this direction. Getting it? Simple.
Okay.
That is the only concept you have to use. Tell me, in this case, what will be the field? Is it not in this direction? E plus Q. And E minus Q will be in this direction. Is that understood? This thing, E plus Q and E minus Q, why they are in this direction? Field is always along the line joining. It will be either away from the charge or towards the charge. Only two possibilities are there. So the charge, the sign of the charge will decide whether it will be towards the charge or away from the charge. So it is a positive charge, so it will be away, right? It is a negative charge, so it will be towards.
Yes.
This thing is clear?
Yes.
Now just see this thing here. Can you tell me what is E plus Q? What is the magnitude of E plus Q?
KQ by
AQ by
R square plus A square the whole square.
whole square, correct. And similarly, E minus Q, same thing, exactly same thing. Distance is exactly the same. Just see that you can write it in two steps, like KQ by R1 square, right? So this is equal to KQ by R square plus A square.
The whole square.
Similarly, this will be equal to what? KQ by
KQ by
R2
the
square.
same R square plus A square the whole square.
Yes, this is also the same. This is the thing. Now just see that in this case, they are not. In the previous case, they were both aligned along the same line. That's why plus minus could have could take care of these things. But here you have to use the vector laws. Just see. We will decompose, like we will resolve this vector along two directions. E plus Q, just see that if I draw a line parallel to this thing, I will drop a line perpendicular to this thing. This will be equal to what? E plus Q. Now just see that if this is theta, this will also be theta. I just drew the line parallel to this thing, right? This theta, corresponding angle, this will also be theta. So E plus Q cos theta will be there. And this thing will be, if I drop the perpendicular to this thing, E plus Q sine theta. This thing is clear?
Yes.
Okay. Now I will use a different color. Similarly, we'll do this vector. We will resolve this vector along two directions. So it will be E minus Q cos theta. And this will be E minus Q sine theta. But just see that E plus Q and E minus Q are exactly the same, right? Magnitudes are exactly the same. They are in opposite direction. So if you are doing 10 Newton of force here and 10 Newton of force in the downward direction, what is the net force? 0, right? If you're pulling on an object on two directions from the same force, 10 Newton, 10 Newton, net force is 0. So net field, vertical components, they just get cancelled out. Right? So clearly here in this diagram, are you getting this point here? You got this point? This is the only point you need to understand. Clearly, okay, I'm just writing this down here. You don't have to do this thing in the exam, right? Just understand this thing. Clearly, the vertical components of the vector get cancelled out. Get cancelled out. So only horizontal component. So only horizontal components contribute to the net electric field. So just see that EP will be equal to what? E plus Q cos theta. E plus Q cos theta plus E minus Q cos theta. They are in the same direction. Getting it? They are in the same direction. So we will just be
Yes,
adding
sir.
those two vectors. So here, very simple now, just do it. Now just put the value of E plus Q and E minus Q. This will be equal to what? Simply can we say that E plus Q plus E minus Q cos theta? E plus Q is equal to what? Very simple. They both are equal, right? They both are equal. Can we say that this is just a twice of this thing? So this is just 2kq by r square plus a square whole square cos theta. Now just find out the value of cos theta. Can you tell me what is the value of cos theta here? Cos theta is equal to what? B by h. That is equal to cos theta. B is equal to what? A. And h is equal to what? R1 square. R1 square is equal to what? R square plus A square.
Yes.
So that is cos theta. Put this value over here. A by 2kq 2kq r square plus A square whole square times A plus A by r square plus A square square root, right? Okay, mind it. This will be just this thing, right? Okay, my mistake. This will be this, right? Our mistake. That was the mistake. Did you get it?
Okay.
R1 root over r square plus a square, right? Not r square plus a square. R1 square will be equal to r square plus a square. So R1 will be equal to a root over r square plus a square, right? This is the thing. This will be, the square of this thing will be like this. So again, now just let us just correct this thing. This square is not there. So 2qa. Can we say this thing? This is simply kp. And simply this is r square plus a square 3 by 2. Right? Power is 1 and here the power is half. So 1 plus half is equal to what? 3 by 2, right? This is the thing.
Okay.
So power is this thing. Clearly EP is equal to this much. General expression for the electric field at the axial point. General expression for the electric field at equatorial plane. Let's just complete this thing. If
Okay.
R is much greater than A, tell me, EP will be reduced to what? You tell me.
R cube. KP by R cube.
AP by R cube. Right? This is the thing. So this is this thing, right? EP is equal to this thing. Clearly, you can see this thing. Clearly, EX, just see that. EX is equal to what? 2 kp by R cube. And E equatorial is equal to what? Kp by R cube. What is the relation between them? Can we say this thing? That EX axial is equal to 2 times E equatorial. Sometimes this relation is asked in the exam. establish the relation that twice of equatorial electric field is equal to axial electric field. Right? And what is the direction of this field? Just tell me, what is the direction? In this case, one more thing here. Electric dipole moment is always negative to positive. Dipole moment is in this direction. But electric field is always coming out to be in this direction, right? Electric field, net electric field, they are
Yes.
opposite. So in this case, in the
So
vector
electric
notation,
field and dipole moment are always opposite.
always opposite. So in this case, just if you express this vector, this was p cap. If you do this thing, minus p cap, right? That's it.
Okay.
This is done. So we have done these two very important derivations. These are very important from exams point of view. So do revise these things, right?
Okay.
So next class we'll do flux and flux and Gauss law. Okay. Okay, then that's it for today. Bye. Do you have any question?
So I'm not able to hear you.
No. Is it audible now?
I can hear now.
Okay. Any question from today's session?
No, sir.
Okay, then see you next class. There we will talk about electric flux. Okay.
Okay.